In early 1995, two Swiss astronomers named Michel Mayor and Didier Queloz made a discovery that would fundamentally alter humanity's understanding of its place in the cosmos. Using a telescope in southern France, they detected something that had eluded astronomers for centuries: the first confirmed planet orbiting a sun-like star beyond our solar system. The planet they found was nothing like Earth. It was a scorching gas giant called 51 Pegasi b, roughly half the mass of Jupiter, completing an orbit around its star in just 4 days. It was far too hot, far too massive, and far too close to its star to harbor anything resembling life as we know it. But none of that mattered. What mattered was that it existed at all. For the first time in human history, we had a proof that our solar system was not unique, that planets orbiting other stars were not just theoretical possibilities, but physical realities waiting to be discovered. Fast forward to today, and the floodgates have opened. We've now confirmed the existence of over 5,000 exoplanets scattered across our corner of the Milky Way galaxy. Rocky worlds smaller than Earth, gas giants larger than Jupiter, ice planets covered in frozen methane, worlds made almost entirely of carbon, with the diamond mantles hidden beneath their surfaces, planets orbiting the remnants of dead stars, rogue planets drifting through the void with no star to call home, wandering the galaxy in eternal darkness. The sheer diversity of worlds out there is staggering, and we've only just begun to scratch the surface. But among this vast cosmic menagerie of alien worlds, there exists a special category of planets that captures our imagination more than any other. Worlds that sit in that perfect Goldilocks zone around their stars, where temperatures are just right for liquid water to flow. Planets with stable climates, protective atmospheres, and the right chemical ingredients for life to take hold. Places that might not just host simple microbial organisms, but entire ecosystems, complex biospheres, perhaps even intelligent civilizations looking up at their own night skies and wondering if they're alone. And here's where things get truly mind-bending. Some of these worlds we've discovered aren't just similar to Earth. According to the math, according to the measurements, according to every metric we use to evaluate habitability, some of these planets might actually be better suited for life than our own world. More stable star systems, longer habitable lifespans, thicker protective atmospheres, calmer stellar environments. In every meaningful way, superior homes for life to evolve and thrive. So let's embark on a journey across the galaxy to visit the most habitable planets humanity has ever discovered, worlds ranked by their potential to support life as we know it. What we're about to find might fundamentally challenge your assumptions about Earth being special, about our planet being perfectly designed for life. Because the evidence increasingly suggests that Earth 2.0 isn't just out there somewhere, waiting to be discovered in some distant future. We may have already found it. Before we can properly tour these alien worlds and understand what makes them special, we need to establish what habitability actually means. And it all starts with something deceptively simple: location. Every star in the universe, whether it's a massive blue supergiant or a dim red dwarf, is surrounded by what astronomers call the habitable zone. You might have heard it referred to as the Goldilocks zone, after the fairy tale character who preferred things not too hot and not too cold, but just right. This is the orbital region around a star where temperatures fall within a specific range that allows liquid water to exist on a planet's surface. Not water vapor, not ice, liquid water. It's perhaps the single most important requirement for life as we understand it. Too close to the star, and your planet gets blasted with so much heat and radiation that any water boils away into space, leaving behind a desiccated husk. Too far from the star, and temperatures plummet so low that everything freezes solid, locking any water away in glaciers and polar caps, unavailable for the chemistry of life. Our own solar system provides a perfect case study in how critical this positioning is. The Sun's habitable zone extends from roughly 0.95 astronomical units to 1.37 astronomical units. An astronomical unit is simply the average distance between Earth and the Sun, about 150 million kilometers. Earth sits comfortably at exactly 1 astronomical unit, right in the sweet spot of this habitable range. We receive just the right amount of stellar energy to maintain liquid oceans covering 70% of our surface. Venus, our planetary neighbor, orbits at 0.72 astronomical units. It's just a bit too close to the Sun, and that slight difference has catastrophic consequences. The extra solar energy Venus receives created a runaway greenhouse effect billions of years ago. Today, its surface temperature exceeds 450 degrees Celsius, hot enough to melt lead. Its atmosphere is a crushing hellscape of carbon dioxide 90 times thicker than Earth's atmosphere, with clouds of sulfuric acid raining down. If there was ever water on Venus, it's long gone, boiled away and lost to space. On the other side of the equation, we have Mars, orbiting at 1.52 astronomical units. It's positioned just slightly too far from the Sun's warmth. Mars used to have liquid water on its surface billions of years ago. We can see the dried-up river channels, the ancient lake beds, the mineral deposits that only form in the presence of water. But Mars is small, with weak gravity, and no global magnetic field to protect it. Over billions of years, the thin Martian atmosphere was gradually stripped away by solar wind. And as the atmosphere thinned, temperatures dropped, and any remaining water froze or evaporated. Today, Mars is a cold desert world, with an average surface temperature of minus 60 degrees Celsius. But here's the crucial thing to understand. Liquid water alone is not sufficient for habitability. It's merely the starting point, the first box to check on a very long list of requirements. A truly habitable world needs so much more than just the right distance from its star. First and foremost, the planet needs to be rocky, not gaseous. Gas giants like Jupiter and Saturn, no matter where they orbit, can't support surface-dwelling life because they don't have a surface to dwell on. Life as we know it requires solid ground, or at least a liquid ocean with a solid core beneath. The planet needs a stable orbit that doesn't send it careening between temperature extremes. An orbit that's too elliptical means the planet spends part of its year freezing and part of it roasting, making it nearly impossible for complex ecosystems to establish themselves. The planet's mass needs to fall within a specific range. Too small, and like Mars, it can't hold on to an atmosphere. The gases simply drift off into space. Too large, and you end up with a super-Earth so massive that its atmosphere becomes a crushing weight, with surface pressures potentially reaching thousands of times Earth's atmosphere. A magnetic field is essential. Earth's magnetic field, generated by the churning of molten iron in our planet's core, creates a protective bubble around our world that deflects most of the dangerous charged particles streaming out from the Sun. Without this shield, solar wind would gradually strip away our atmosphere, just like it did to Mars. the planet needs the right chemical inventory. Carbon, the backbone of all organic molecules. Oxygen for energy metabolism. Nitrogen for proteins and DNA. Phosphorus for cellular energy transfer. Without these building blocks, life as we know it simply cannot assemble itself. And perhaps most critically, the planet needs time. Vast stretches of geological time for chemistry to give rise to biology, for simple organisms to evolve into complex ones. Life first appeared on Earth roughly 3.8 billion years ago, shortly after the planet cooled enough to have liquid oceans. But for the next 3 billion years, that life consisted entirely of single-celled microorganisms, bacteria, archaea, simple things floating in ancient seas. It took 3 billion years before multicellular organisms evolved. It took nearly 4 billion years before complex life colonized the land. Intelligence, tool use, civilization, that only emerged in the last few million years, a blink of an eye on geological timescales. What this means is that a planet orbiting a star that's only a few 100 million years old, no matter how perfect its conditions might be, probably isn't home to a thriving civilization. There simply hasn't been enough time for intelligence to evolve. To help quantify all these factors, scientists developed something called the Earth Similarity Index. It's a mathematical formula that produces a score between 0 and 1, where 1 represents a planet identical to Earth in every measurable way. The index considers factors like planetary radius, density, escape velocity, and surface temperature. It's not a perfect measure of habitability by any means, because it doesn't account for things like atmospheric composition, magnetic fields, or stellar activity. But it gives us a useful starting point for comparing exoplanets to our home world. Earth, by definition, scores a perfect 1.0 on this scale. Mars, despite being in our own solar system and having once hosted liquid water, scores only 0.697. Venus, our so-called sister planet with almost identical size and mass to Earth, scores 0.444 because its surface conditions are so hellishly extreme. Now, here's where things get interesting. Several exoplanets we've discovered score above 0.8 on the Earth Similarity Index. They're more Earth-like than any other planet in our own solar system except Earth itself. And when you factor in additional considerations beyond the basic index, things like the stability and longevity of the host star, the age of the planetary system, the likelihood of maintaining a protective magnetosphere over billions of years, some of these worlds actually receive higher habitability scores than Earth. Let me repeat that because it's worth emphasizing. We have found planets that, according to our best scientific understanding, might be even better suited to hosting life than our own world. They orbit more stable stars. They exist in calmer stellar environments with less radiation bombardment. Their habitable conditions might persist for tens of billions of years, far longer than Earth's estimated remaining habitable lifetime of perhaps 1 billion years, before our sun's gradually increasing luminosity triggers a runaway greenhouse effect and turns us into Venus. These aren't just planets where life could theoretically exist. These are worlds where life might have an even better chance of arising, evolving, and surviving than it did here. So, let's meet them. Let's visit these remarkable worlds and understand what makes each one special, what advantages they might have over Earth, and what challenges they face. Our first destination takes us 1,200 light-years from Earth to a world orbiting a star in the constellation Lyra. The planet is called Kepler 442b, and right from the start, this world does something remarkable. it beats Earth's habitability score. Not by a small margin either. By enough that scientists have called it one of the most potentially habitable exoplanets ever discovered. Kepler 442b is what astronomers classify as a super-Earth, a term that sounds more impressive than it actually is. It simply means a rocky planet more massive than Earth, but smaller than the ice giants Uranus and Neptune. This particular super-Earth has about 2.3 times Earth's mass and 1.3 times its radius. It's definitively rocky, not a puffy gas planet, and its increased size comes with some significant advantages we'll get to in a moment. But what truly sets Kepler 442b apart isn't the planet itself. It's the star it orbits. Kepler 442 is what astronomers call an orange dwarf, also known as a K-type main sequence star. It's smaller than our Sun, cooler than our Sun, and, most importantly, more stable than our Sun. And that stability makes all the difference in the universe. You see, our Sun is what scientists would politely describe as temperamental. It has sunspots that come and go in 11-year cycles. It produces solar flares, sudden eruptions of electromagnetic radiation that can disrupt satellites and power grids here on Earth. It occasionally hurls billion-ton clouds of plasma into space through coronal mass ejections. These events are dramatic, powerful, and potentially devastating to planetary atmospheres. A strong enough solar flare directed at a planet can strip away portions of its atmosphere over time, gradually eroding the protective blanket of gases that keeps the surface habitable. Mars likely lost much of its atmosphere this way, unable to defend itself without a global magnetic field. Kepler 442, being an orange dwarf, is far more sedate. It still produces some stellar activity, of course. All stars do, but the frequency and intensity of its outbursts are dramatically lower than what our Sun dishes out. Less extreme radiation, fewer violent flares. A calmer, more predictable stellar environment. For life trying to gain a foothold on a planet, this kind of stellar stability is invaluable. But here's where it gets even better. Orange dwarfs have much longer lifespans than stars like our Sun. Our Sun will remain stable and habitable for about 10 billion years total. It's currently about 4.6 billion years old, meaning it has roughly 5 billion years left before it begins its evolution into a red giant, expanding outward and eventually engulfing the inner planets. 5 billion years sounds like a lot, and it is. But orange dwarfs can shine steadily for 30 billion years or more. That's 3 times longer than our Sun's entire main sequence lifetime. 3 times longer for planets in their habitable zones to develop life. 3 times longer for that life to evolve from simple chemistry to complex organisms. 3 times longer for intelligence to emerge, for civilizations to rise. Kepler 442b orbits its star every 112 days, completing more than 3 orbits for every 1 Earth year. Because its star is cooler and dimmer than the Sun, the planet has to orbit much closer to receive the same amount of stellar energy. But this close orbit doesn't mean scorching temperatures. Studies suggest the planet's surface temperature could average anywhere from 0 to 15 degrees Celsius if it has an Earth-like atmosphere. Think of a world in perpetual autumn. Cool but not freezing. Temperate but not tropical. The kind of climate where liquid water could exist in abundance across much of the surface. Now, let's talk about those advantages that come with being a super-Earth. The increased mass means stronger surface gravity, about twice what we experience on Earth. That might sound unpleasant, and for human visitors it would certainly take some getting used to. But for the planet itself, stronger gravity is a tremendous asset. It means a thicker atmosphere. All planets lose atmospheric gases to space over time through a process called atmospheric escape. Lighter molecules, particularly hydrogen and helium, can reach high enough velocities to break free of a planet's gravitational pull and drift away forever. Mars lost most of its atmosphere this way because its gravity is only about 38% of Earth's, too weak to hold on. But Kepler 442b's stronger gravity creates a much tighter grip on its atmospheric gases. It can maintain a thicker atmosphere over billions of years, even in the face of stellar wind and radiation trying to strip it away. A thicker atmosphere provides better insulation, keeping surface temperatures more stable. It provides better protection from cosmic radiation and small meteorites that would burn up in the thick air before reaching the ground. It also means the planet is less vulnerable to the kind of atmospheric collapse that doomed Mars. Computer models that simulate planetary climates over geological timescales have produced some fascinating results for Kepler 442b. If the planet has an Earth-like atmospheric composition, primarily nitrogen and oxygen with traces of carbon dioxide and water vapor, and if it has geological activity similar to Earth's plate tectonics and volcanic outgassing to recycle carbon and regulate climate, then it could maintain liquid water on its surface for the entire lifespan of its star. Not just the next few billion years, not just 10 or 20 billion years, but potentially for 30, 40, even 50 billion years into the future. Long after our sun has died, long after Earth has been reduced to a cinder or swallowed entirely, Kepler 442b could still have oceans lapping against alien shores under a rust-colored sky. The planet scores an Earth Similarity Index of 0.836, one of the highest values ever calculated for an exoplanet. To put that in perspective, that's higher than Mars at 0.697, higher than Venus at 0.444, more Earth-like than any world in our own solar system except Earth itself. Of course, we need to be honest about what we don't know, and the list of unknowns is substantial. We don't actually know if Kepler 442b has an atmosphere at all. We've never directly detected one. The planet was discovered using the transit method, where astronomers measure the tiny dip in starlight when a planet passes in front of its star from our perspective. This method tells us the planet's size and orbital period, but it doesn't reveal atmospheric composition. Not yet anyway. We don't know what that atmosphere might be made of if it exists. Is it nitrogen and oxygen like Earth? Carbon dioxide like Venus? Methane and ammonia? A toxic soup of hydrogen sulfide? Each composition would create radically different surface conditions. We can't definitively confirm the planet is rocky, though its measured mass and radius make that almost certain. There's a small possibility it could be more like a mini Neptune, with a small rocky core surrounded by a thick envelope of hydrogen and helium. But the numbers don't really support that interpretation. We have no way of knowing whether the planet has the geological activity necessary to maintain long-term habitability. On Earth, plate tectonics plays a crucial role in regulating climate by recycling carbon dioxide between the atmosphere, oceans, and rocks. Volcanic eruptions replenish atmospheric gases that would otherwise be lost. Without these processes, even a planet in the perfect location could become uninhabitable over time. We don't know if it has a magnetic field to protect against stellar radiation. We don't know if it has water, and if so, how much. Is it a desert world with small polar ice caps? An ocean planet with water covering 90% of the surface? Something in between like Earth? And we certainly don't know if life exists there, let alone what form that life might take. But here's the thing. Based purely on what we do know, on the measurable facts about this planet's size, mass, orbit, and stellar environment. If you were an engineer tasked with designing a planet specifically optimized for the maximum potential to host life over the longest possible time span, Kepler 442b would be a pretty damn good blueprint. More mass for atmospheric retention, a more stable star for consistent conditions, a longer stellar lifetime for evolution to work its slow magic. This world has so many factors working in its favor that it's hard not to imagine oceans and continents and life taking advantage of those favorable conditions. Of course, there's one rather significant problem with Kepler 442b. It's 1,200 light-years away. At our current level of technology, that distance is essentially unreachable. Our fastest spacecraft, the Parker Solar Probe, travels at about 190 kilometers per second when it's at top speed during close approaches to the Sun. At that velocity, it would take roughly 2 million years to reach Kepler 442b. 2 million years. Human civilization has only existed for a tiny fraction of that time. We might develop faster propulsion systems in the future. Nuclear, pulse propulsion, antimatter drives, something we can't even imagine yet. But even with wildly optimistic technological advances, interstellar travel to a star system 1,200 light-years away remains firmly in the realm of science fiction for now. Which brings us to an obvious question. What about planets closer to home? What about worlds we could actually reach, or at least study in detail with our telescopes? What about the exoplanet that orbits the nearest star to our Sun? Enter Proxima Centauri b. At just 4.24 light-years from Earth, Proxima Centauri b is our closest exoplanetary neighbor. It orbits Proxima Centauri, a red dwarf star that's part of the Alpha Centauri system, a triple star system visible from Earth's southern hemisphere. Alpha Centauri has captivated human imagination for generations, precisely because of its proximity. It's been the target of countless science fiction stories, the destination of hypothetical interstellar missions, the place we'd logically explore first if we ever developed the capability. And now we know it has planets. Proxima Centauri b was discovered in 2016 after years of careful observation. It has a minimum mass of about 1.17 times Earth's mass, making it potentially just slightly larger than our world. The word minimum is important here because the method used to detect it, measuring the tiny wobble in the star's motion caused by the planet's gravity, only tells us the lower bound on mass. The actual mass could be somewhat higher, depending on the planet's orbital inclination. The planet orbits its star every 11.2 days. Yes, you read that correctly. Its entire year, one complete orbit around its Sun takes just 11 Earth days. That sounds impossibly close, impossibly hot, but remember that Proxima Centauri is a red dwarf, much smaller and cooler than our Sun. Red dwarfs are the universe's misers, burning their nuclear fuel so slowly and efficiently that they can shine for trillions of years. But the trade-off for that longevity is that they're dim. Very dim. Proxima Centauri produces only about 0.17% of the Sun's luminosity. So, for a planet to receive enough energy to maintain liquid water, it has to orbit very close indeed. And Proxima b does exactly that, sitting right in the middle of its star's habitable zone. If the planet has an Earth-like atmosphere, Surface temperatures could range anywhere from -50 to +30 degrees Celsius, depending on atmospheric thickness and composition. Not exactly tropical, but certainly within the range where life as we know it could survive. The planet scores an Earth Similarity Index of around 0.85, right up there with Kepler 4.4.2b, in terms of how Earth-like its basic properties are. But what truly sets Proxima Centauri b apart from every other potentially habitable exoplanet we've discovered is one simple fact. We could actually go there. Not today. Not with current technology, but within the realm of plausible near-future engineering. In 2016, the same year Proxima b was discovered, a project called Breakthrough Starshot was announced. Backed by physicist Stephen Hawking and billionaire Yuri Milner, the initiative proposes sending thousands of tiny spacecraft, each weighing just a few grams, to Alpha Centauri. These miniature probes would be equipped with light sails, thin reflective sheets that can be pushed by powerful laser beams. The idea is to build an enormous ground-based laser array that would fire concentrated light at these tiny spacecraft, accelerating them to about 20% of the speed of light. At that velocity, the probes could reach Proxima Centauri in roughly 20 years. Once there, they'd take photographs, make measurements, gather data, and beam it all back to Earth. The signal would take another 4.2 years to reach us, meaning we could have actual close-up images of an Earth-sized exoplanet within about 25 years of launch. Within a single human lifetime, we could go from discovering this planet exists to photographing it up close. That's not science fiction. That's engineering. Difficult engineering, certainly, requiring technological advances in laser power, miniaturization, and data transmission. But nothing that violates the laws of physics. Nothing that requires exotic matter or warp drives or wormholes. Just really good engineering and a lot of money. But proximity comes with its own set of challenges, and for Proxima Centauri b, those challenges are significant. Red dwarfs might burn steadily for trillions of years, but that doesn't mean they're calm. In fact, in many ways, they're the opposite. Red dwarfs are notorious for producing violent stellar flares, sudden eruptions of energy and charged particles that can increase a star's brightness by factors of 10 or even 100 within minutes. These aren't the relatively mild solar flares we experience from our sun. These are orders of magnitude more powerful, and they happen far more frequently. In March 2016, just a few months before Proxima Centauri b was announced to the world, astronomers observed Proxima Centauri unleashing a superflare that increased the star's brightness by 68 times its normal luminosity for several minutes. The amount of high-energy radiation released during that event was staggering. If Proxima b happened to be in the direct path of that flare, and given its close orbit it almost certainly was, the planet would have been bathed in radiation levels far exceeding anything life on Earth has ever experienced. X-rays, extreme ultraviolet light, charged particles, all of it slamming into the planet's atmosphere at point-blank range. Now, here's the critical question. Does Proxima b have a strong magnetic field to protect itself? Earth's magnetic field deflects most of the charged particles from solar flares, channeling them toward the poles where they create the auroras. Without that protection, our atmosphere would be gradually stripped away, molecule by molecule, until nothing remained but bare rock. We simply don't know if Proxima b has a protective magnetic field. We have no way to measure it from here. If it does, the planet might weather these stellar storms relatively unscathed, maintaining its atmosphere over billions of years despite the frequent bombardment. If it doesn't, every flare could be an extinction-level event, sterilizing the surface over and over again. Perhaps life exists deep underground, in subsurface oceans protected from the radiation. Perhaps it doesn't exist at all. Then there's the issue of tidal locking. When a planet orbits very close to its star, gravitational forces create tidal bulges, similar to how the Moon creates tides in Earth's oceans. Over time, these tidal forces slow down the planet's rotation until it becomes synchronized with its orbital period. The result is tidal locking, where the planet always shows the same face to its star, just like the Moon always shows the same face to Earth. Proxima Centauri b almost certainly experienced this process billions of years ago. One hemisphere perpetually faces the star, bathed in eternal daylight. The other hemisphere faces away, plunged into eternal darkness. No day-night cycle, no sunrise or sunset, just permanent noon on one side and permanent midnight on the other. The day side would likely become a scorching desert as any water evaporates under the constant stellar heat. The night side would freeze into a glacial wasteland as temperatures plummet without any warmth from the star. Between them, a narrow band of twilight, where the star sits permanently on the horizon. This twilight zone might be the only place on the entire planet where temperatures are moderate enough for liquid water to exist. But here's where things get interesting, because tidal locking might not be the death sentence it initially appears to be. Climate models suggest that if Proxima b has a thick enough atmosphere, heat from the day side could be transported to the night side through atmospheric circulation. Think of it like a giant heat engine. Hot air rises on the day side, flows high in the atmosphere toward the night side, cools and sinks, then flows back along the surface toward the day side. This circulation pattern could redistribute heat across the entire planet, preventing the temperature extremes that would otherwise make tidal-locked worlds uninhabitable. Some models suggest this could create a surprisingly temperate climate across the whole planet, with only moderate temperature variations between the eternal day and eternal night. Other models are less optimistic, suggesting the night side would still be cold enough to freeze out most of the atmosphere itself, with carbon dioxide and nitrogen condensing into ice and accumulating in massive polar caps on the dark side. The redistribution of heat might not be sufficient to prevent this atmospheric collapse. We won't know which scenario is correct until we can actually study the planet's atmosphere, which brings us back to the James Webb Space Telescope and future observatories. There's also speculation about water. Lots of water. If Proxima b formed further out in its solar system, beyond the frost line where water ice could exist, and then migrated inward over millions of years, it could have started life as an icy world covered in frozen oceans. As it moved closer to the star and entered the habitable zone, all that ice would have melted, potentially creating a true ocean world with water hundreds or even thousands of kilometers deep covering the entire surface. A planet where land is non-existent, and life, if it exists, would be entirely aquatic. No continents, no mountains, just endless ocean beneath an alien sky, with the dim red sun hanging motionless at the zenith if you're on the day side, or a sky full of stars if you're on the night side. And Proxima Centauri b might not be alone. In 2020, additional observations provided evidence for a second planet in the system, designated Proxima c, orbiting much farther out where temperatures are far too cold for liquid water. Then, in 2022, another candidate planet emerged from the data, this one called Proxima d. orbiting even closer to the star than Proxima b. If these additional planets are confirmed, Proxima Centauri would be a multi-planet system, our nearest stellar neighbor hosting multiple worlds. What makes Proxima Centauri b truly special isn't just its Earth-like properties or its position in the habitable zone. It's the simple fact that we might actually detect signs of life there within our lifetimes. Next-generation telescopes could analyze the planet's atmosphere, searching for biosignatures like oxygen and methane existing together, ozone layers that indicate photosynthetic life, or even industrial pollutants that would prove the existence of a technological civilization. We're living in the generation that could answer whether our nearest neighboring star system hosts life. That's extraordinary. But if you think one potentially habitable planet in our cosmic neighborhood is exciting, let me tell you about a star system that doesn't just have one Earth-like world. It has 7, and 3 of them are in the habitable zone. In February 2017, NASA held a press conference that sent shockwaves through the scientific community and dominated headlines around the world. Astronomers had discovered something unprecedented: 7 Earth-sized planets orbiting a single star. Not gas giants, not super-Earths. Earth-sized, rocky, and 3 of them sitting comfortably in the habitable zone where liquid water could exist. The star is called TRAPPIST-1, named after the telescope that discovered it, the Transiting Planets and Planetesimals Small Telescope. It's an ultra-cool red dwarf located about 40 light-years from Earth in the constellation Aquarius. When I say ultra-cool, I mean it quite literally. TRAPPIST-1 has a surface temperature of only about 2500 Kelvin compared to the Sun's 5700 Kelvin. It's tiny, with only about 9% of the Sun's mass and roughly the size of Jupiter. If you could somehow place TRAPPIST-1 in our solar system, all 7 of its planets would fit comfortably within the orbit of Mercury. The innermost planet would orbit closer to TRAPPIST-1 than Io orbits Jupiter. The outermost planet would still be closer than Mercury is to our Sun. It's an impossibly compact system by the standards we're used to, and yet it works. The 7 planets are designated TRAPPIST-1b through H, moving outward from the star. Planets B and C are too close, receiving too much stellar heat for water to remain liquid. Planet H is too far out, locked in permanent deep freeze. But planets D, E, F, and G, they're all in the habitable zone. 4 potentially habitable worlds in a single star system. But the crown jewel, the planet that seems to have the best combination of properties, is TRAPPIST-1e, the 4th planet from the star. This world is remarkably similar to Earth in size and mass, about 91% of Earth's radius and 62% of its mass. Its density suggests a rocky composition with a substantial iron core, similar to Earth's internal structure. And here's the kicker. It receives approximately the same amount of stellar energy that Earth receives from the Sun. Not more, not less. Almost exactly the same. If TRAPPIST-1e has an atmosphere similar to Earth's, its surface temperatures would be nearly identical to ours. The planet completes an orbit every 6.1 days. That sounds extreme until you remember that TRAPPIST-1 is so cool and dim that its habitable zone is incredibly close to the star. The planet orbits at a distance of only 0.029 astronomical units, more than 30 times closer than Earth orbits the Sun. At that distance, the planet is almost certainly tidally locked, always showing the same face to its star. But, as we discussed with Proxima b, that might not be the deal-breaker it initially seems. What makes TRAPPIST-1e special What makes the entire system special is something called orbital resonance. All 7 planets are locked in a gravitational dance where their orbital periods are related by simple mathematical ratios. For every 2 orbits planet E completes, planet D completes exactly 3. For every 3 orbits planet Io completes, planet F completes exactly 2. These resonances extend through the entire system, creating a precisely synchronized ballet of worlds. It's like a cosmic symphony where every instrument hits its note at exactly the right moment, over and over again, for billions of years. This orbital choreography has profound implications for stability. The planets are constantly tugging on each other gravitationally, but they do so in a perfectly balanced way that prevents the system from falling apart. No collisions, no ejections, just stable orbits maintained through gravitational harmony. This resonance chain has kept the TRAPPIST-1 system stable for billions of years, and will likely continue to do so for billions more. But here's where the TRAPPIST-1 system becomes truly mind-bending. The planets orbit so close together that if you stood on the surface of TRAPPIST-1e and looked up at the sky, you wouldn't just see stars twinkling in the darkness. You would see the neighboring planets, and not as tiny points of light like we see Venus or Mars from Earth. Some of them would appear larger than the Moon appears from Earth. TRAPPIST-1f, the next planet out, would loom overhead like a massive celestial body, its features potentially visible to the naked eye. You might see clouds swirling in its atmosphere. You might see continents and oceans if they exist. You might see the lights of cities if anyone lives there. During certain orbital alignments, you might see multiple planets at once, hanging in the sky like ornaments. Imagine the psychological impact that would have on any intelligent species that evolved there. On Earth, we looked up at the Moon, a dead, airless rock, and dreamed for thousands of years about going there. It took us from the first human civilizations to 1969 to make that dream reality. But on TRAPPIST-1e, neighboring habitable worlds would be staring you in the face every single night. Some of them potentially showing obvious signs of life, green and blue and white with vegetation and oceans and clouds. The drive to reach them wouldn't just be scientific curiosity, it would be an overwhelming psychological imperative. And here's the remarkable thing. It would actually be easier than reaching the Moon from Earth. The distances between the TRAPPIST-1 planets are measured in millions of kilometers, not the billions that separate planets in our solar system. With current rocket technology, not some hypothetical future propulsion system, but the chemical rockets we use today, a spacecraft could travel from TRAPPIST-1e to TRAPPIST-1f in a matter of weeks. Not years, not decades, weeks. Any civilization that arose in the TRAPPIST-1 system would have multiple habitable worlds within easy reach. They could establish colonies on neighboring planets using technology barely more advanced than what we have now. They could build an interplanetary civilization while still in the early stages of spaceflight. They wouldn't need generation ships or suspended animation or any of the science fiction solutions we contemplate for interstellar travel. They'd just need patience and good rockets. TRAPPIST-1. E scores an Earth Similarity Index of 0.85, tied with Proxima Centauri b as one of the most Earth-like worlds ever discovered. Studies analyzing the planet's likely composition, orbital dynamics, and stellar environment suggest it could very well have a substantial atmosphere, possibly similar to Earth's nitrogen-oxygen mix, though we won't know for certain until we can directly observe it. And that's exactly what we're trying to do. The James Webb Space Telescope has already observed the TRAPPIST-1 system multiple times, analyzing starlight as it filters through the planet's atmospheres during transits. The initial observations ruled out thick hydrogen-dominated atmospheres for the inner planets, which is actually excellent news. Thick hydrogen atmospheres would indicate puffy mini-Neptunes rather than rocky terrestrial worlds. The fact that we're not seeing them means these planets are more likely to have thin, rocky planet atmospheres like Earth, Venus, or Mars. In the coming years, Webb will continue observing these worlds, searching for the chemical fingerprints of gases in their atmospheres: oxygen, methane, water vapor, carbon dioxide, ozone. Each of these molecules absorbs light at specific wavelengths, leaving dark lines in the spectrum that we can detect from 40 light-years away. If we find oxygen and methane together in significant quantities, that would be a strong biosignature, because these gases react with each other and disappear unless something is continuously replenishing them. On Earth, that something is life. If any of the TRAPPIST-1 planets harbor life, we might actually detect it within the next decade. Not by sending probes there, not by waiting for radio signals, just by analyzing the chemistry of their air and finding combinations of gases that can't be explained by geology alone. We're living in the era when this becomes possible, and the TRAPPIST-1 system is one of our best targets. But let's move on from our stellar neighbors and talk about a planet that's been called Earth's cousin. A world so similar to our own that it orbits a near twin of our Sun at almost the same distance Earth does, taking almost exactly 1 Earth year to complete its orbit. In July 2015, NASA held a press conference to announce what they described as the most Earth-like planet yet discovered. They called it Kepler 452b, and the parallels to our homeworld are almost eerie. The planet is located 1,400 light-years away in the constellation Cygnus, the Swan. It orbits a star called Kepler 452, and that star is so similar to our Sun that if you swapped them, you might not even notice. Kepler 452 is only 4% more massive than the Sun, 10% larger in radius, and about 20% more luminous. Those are tiny differences on astronomical scales. For all practical purposes, it's a solar twin. And Kepler 452b's orbital period? 385 days. Earth's orbital period is 365 days. If you lived on Kepler 452b and used an Earth calendar, you'd celebrate your birthday only 20 days earlier each year. The planet itself is larger than Earth, about 60%, greater in diameter, and estimates suggest it could be roughly 5 times more massive. That places it firmly in the super-Earth category, similar to Kepler 442b. Computer models suggest it's almost certainly rocky rather than gaseous, with a thick atmosphere held in place by stronger gravity. Its position within the habitable zone of a Sun-like star gives it an Earth Similarity Index of around 0.83. But here's what really sets Kepler 452b apart from every other planet we've discussed so far. Age. The Kepler 452 system is approximately 6 billion years old. Our solar system, by comparison, is 4.6 billion years old. Kepler 452b has a 1.5 billion year head start. Now, 1.5 billion years might not sound like much in the grand scheme of cosmic time, but in evolutionary terms, it's absolutely enormous. Consider what happened on Earth over the past 1.5 billion years. 1.5 billion years ago, Earth was in the Mesoproterozoic era. Life at that time consisted entirely of single-celled organisms. bacteria and archaea floating in primordial seas. There were no plants, no animals, no fungi, no multicellular life of any kind. The atmosphere contained very little oxygen. The continents were barren rock, completely devoid of life. Then, about 1.2 billion years ago, something revolutionary happened. A few lineages of organisms figured out how to stick together, forming the first multicellular structures. It took hundreds of millions more years for complex multicellular life to truly diversify. About 600 million years ago, in an event called the Cambrian explosion, animal life suddenly erupted into incredible diversity. Life colonized the land about 450 million years ago. Dinosaurs ruled the Earth for over 160 million years before being wiped out 66 million years ago. Mammals diversified to fill the empty niches. Primates emerged. Hominids appeared just a few million years ago. Modern humans have only existed for about 300,000 years. Civilization is merely 10,000 years old. All of that happened in 1.5 billion years, the evolution from single cells to space telescopes. If Kepler 452b formed with liquid water and the right chemistry for life, and if life arose there at roughly the same time it arose on Earth relative to the planet's formation, and if that life followed a similar evolutionary trajectory, then Kepler 452b could be 1.5 billion years ahead of us in biological and potentially technological development. What could a civilization achieve with a 1.5 billion year head start? Could they have spread to neighboring star systems? Could they have engineered their own biology? Could they have transcended physical form entirely? Or perhaps the evolutionary path on Kepler 452b was completely different. Perhaps life arose later or evolved more slowly, or never developed intelligence at all. Perhaps intelligence arose and destroyed itself in a nuclear war or ecological collapse, and the planet is now home to nothing but radioactive ruins and silent oceans. Evolution doesn't follow a predetermined script. There's no guarantee that intelligence emerges at all, let alone at any particular time. Earth's evolutionary history is marked by random catastrophes that wiped out most life and allowed different lineages to dominate. The asteroid that killed the dinosaurs 66 million years ago created the opportunity for mammals to diversify and eventually produce primates. Without that cosmic accident, intelligent dinosaurs might have evolved instead of humans, or intelligence might never have emerged at all. So, while the math is tantalizing, while the idea of a civilization 1.5 billion years more advanced than us captures the imagination, we have to be honest about the speculation involved. But there's another side to Kepler 452b's age, and it's not as optimistic. Stars don't shine at constant brightness throughout their lifetimes. They gradually brighten as they age, a consequence of changes in their core as hydrogen fuses into helium and the stellar structure adjusts. Our Sun, for instance, has increased in luminosity by about 30% since it first ignited 4.6 billion years ago. Over the next billion years, it will continue to brighten, pumping more and more energy into Earth's climate system. Eventually, probably within the next billion years, this gradual brightening will trigger a runaway greenhouse effect. Earth's oceans will evaporate. Water vapor will fill the atmosphere, trapping more heat, which evaporates more water, which traps more heat, in a vicious feedback loop. Earth will transform into a hellish copy of Venus, with surface temperatures hot enough to melt lead, and an atmosphere so thick it would crush any probe that tried to land. It's the inevitable fate of every planet in the habitable zone. Habitability is temporary. Every world is caught in a race between the formation of its star and its death, between the cooling of the young planet and the brightening of the aging star. Kepler 452b's star, being 1.5 billion years older than the Sun, has gone through more of this brightening process. It's about 20% more luminous than the Sun right now, pumping more energy into Kepler 452b than Earth receives. Studies of the planet's climate suggest it might already be approaching the inner edge of the habitable zone. Some models indicate it could be entering the early stages of a runaway greenhouse effect right now. If there were oceans on Kepler 452b billions of years ago, they might be slowly evaporating today. Water vapor accumulating in the atmosphere. Surface temperatures creeping upward decade by decade, century by century. The climate becoming increasingly hostile to complex life. If there is a civilization on Kepler 452b, they might be living in the twilight years of their planet's habitability. They might be desperately trying to engineer solutions to a warming world, building massive solar shades in orbit or seeding the atmosphere with reflective particles to bounce sunlight back into space. Or they might be planning their escape, building generation ships to migrate to the outer planets as the inner world becomes uninhabitable, abandoning their ancestral home as it succumbs to the brightening star. It's a haunting scenario and a sobering reminder that habitability isn't a permanent state. Every planet in the universe has a finite window during which conditions are right for life. Earth's window will close in roughly 1 billion years. Kepler 452b's window might be closing right now. Now, let's talk about a planet that took years to reveal its most spectacular secret. When LHS 1140b was first discovered in 2017, it was recognized as a potentially habitable super-Earth orbiting a red dwarf star. Scientists noted it as interesting, potentially important, but it didn't generate the same level of excitement as TRAPPIST-1 or Proxima Centauri b. It was just another entry in the growing catalog of exoplanets, another world to study when telescope time became available. Then, in 2024, everything changed. New observations using the James Webb Space Telescope revealed something extraordinary about LHS 1140b. It's not just a rocky planet with perhaps some surface water like Earth. It might be a true water world, with a global ocean thousands of kilometers deep covering its entire surface. No continents, no islands, just endless ocean under an alien sky. LHS 1140b is located 49 light-years from Earth, orbiting a red dwarf star considerably smaller and cooler than our Sun. The planet itself is 1.73 times Earth's radius and 5.6 times its mass, placing it in the super-Earth category. It orbits its star every 25 days, sitting comfortably within the habitable zone where temperatures could allow liquid water. For years after its discovery, astronomers assumed it was essentially a larger, more massive version of Earth. Rocky interior, probably some water on the surface, maybe oceans covering 60 or 70% of the planet like Earth's oceans do. Then scientists started looking more carefully at the planet's density, and the numbers didn't quite add up. The planet's mass and radius, when combined to calculate density, suggested it was less dense than a pure rock and iron world should be. Something was lowering the average density. Something lighter than rock had to make up a significant portion of the planet's mass. The most likely candidate? Water. A lot of water. Detailed modeling suggests that water could account for 10 to 20% of the planet's total mass. Let me put that in perspective. On Earth, all the water in all the oceans, all the lakes, all the rivers, all the ice caps, all the groundwater, all the water vapor in the atmosphere, everything combined, accounts for about 0.05% of Earth's total mass, half of 0.1%. Water is a tiny component of our planet by mass. Most of Earth is iron core and rocky mantle. But if 10 to 20% of LHS 1140b's mass is water, and if that water is spread across the entire planet's surface rather than locked away in the interior, the resulting ocean would be between 2,000 and 4,000 kilometers deep. Earth's deepest ocean trench, the Mariana Trench, reaches down about 11 kilometers. The average depth of Earth's oceans is about 3.7 kilometers. An ocean 4,000 kilometers deep is more than 1,000 times deeper than Earth's oceans. It's deeper than the distance from New York to Los Angeles. At those depths, the pressure would be absolutely immense, millions of times greater than atmospheric pressure at sea level. But pressure alone doesn't preclude life. We've found organisms thriving in Earth's deepest ocean trenches, in environments where the pressure would instantly crush any human. Pressure is just another environmental parameter that life can adapt to. The upper layers of such an ocean, the top few kilometers where sunlight can still penetrate, could be remarkably Earth-like. Temperate temperatures, abundant water, dissolved minerals and gases, everything needed for life as we know it. Below that, in the perpetual darkness of the deep ocean, life could exist around hydrothermal vents, volcanic structures on the ocean floor that spew superheated, mineral-rich water. On Earth, entire ecosystems thrive around these vents, completely independent of sunlight, deriving their energy from the chemical reactions between the hot vent water and the cold ocean. On a planet like LHS 1140b, if it truly is a water world, evolution would take a completely different path than it did on Earth. There would be no land to colonize, no forests or grasslands or deserts, no terrestrial ecosystems at all. Everything would be aquatic. Life might exist as vast floating mats of photosynthetic organisms near the surface, harvesting sunlight and producing oxygen. Deeper down, filter feeders could process the rain of organic material falling from above. Near the ocean floor, if there's geological activity producing hydrothermal vents, entire ecosystems could thrive in the darkness, powered by chemistry rather than sunlight. And if intelligence evolved on such a world, it would be marine intelligence. Think dolphins or octopuses, but with millions of additional years of evolution. Tool use would be challenging underwater, but not impossible. Fire would be impossible, which would make metallurgy and advanced technology much harder to develop. But perhaps there are other paths to technological civilization that don't require fire. Perhaps a water-world civilization would develop biological technology, engineering organisms to serve as tools. Or perhaps they would discover ways to create air pockets and develop technology there. But here's what really sets LHS 1140b apart from almost every other potentially habitable exoplanet we've found. We can actually study its atmosphere in detail. The James Webb Space Telescope observed LHS 1140b multiple times in 2024, and the data is remarkable. The observations detected potential signs of water vapor in the planet's atmosphere. Not definitive proof yet, because the data requires careful analysis to rule out other explanations. But the signature is there. water vapor would make perfect sense for an ocean world. Evaporation from the vast oceans would continuously pump water into the atmosphere. Some observations also suggested the possible presence of methane. Methane is particularly interesting because it's a potential biosignature. On Earth, the vast majority of atmospheric methane is produced by biological processes: bacteria in wetlands, termites, livestock, human industry. There are geological sources of methane too, like volcanic outgassing and the breakdown of organic material in rocks, but biology is the dominant source. If LHS 1140b has significant methane in its atmosphere, and if we can rule out geological explanations, that would be powerful evidence for life. Not proof, but strong evidence, strong enough to warrant intense follow-up observations. And, unlike many exoplanets, LHS 1140b is particularly well suited for atmospheric studies. Its red dwarf star is relatively quiet, without the extreme flaring that makes observing planets around more active red dwarfs difficult. The planet's size creates deep transits, blocking a relatively large amount of starlight as it passes in front of its star, which gives us more signal to work with. Its 25-day orbit means we get relatively frequent opportunities to observe it. Over the next several years, as Webb continues to observe this planet, and as other next-generation telescopes come online, we'll be able to build an increasingly detailed picture of LHS 1140b's atmosphere. We'll measure the ratios of different gases. We'll look for seasonal variations. We'll search for additional biosignatures. If life exists on this ocean world, we have a genuine chance of detecting it from 49 light-years away. Of course, there are other potentially habitable planets worth mentioning, worlds that didn't quite make our top tier, but are nonetheless fascinating. Kepler 1649c, for instance, has an Earth Similarity Index of 0.75. It's nearly identical to Earth in size and orbits within the habitable zone of a red dwarf star. What makes it particularly interesting is that it was found in old Kepler Space Telescope data that was initially thought to contain nothing. The planet's signal was so subtle, buried so deeply in the noise, that it took years of reanalysis to find it. How many other Earth-like worlds are hiding in data we've already collected but haven't properly analyzed yet? Then there's TOI 700d, another Earth-sized planet orbiting a red dwarf in the habitable zone. It's about 1.2 times Earth's radius and orbits every 37 days. What's notable about TOI 700d is that it's part of a multi-planet system with at least 2 other known worlds, and it might be one of the most precisely measured exoplanets in terms of mass and radius, giving us high confidence in its rocky composition. K218b deserves mention as well, though it's more controversial. It's a mini-Neptune, larger than Earth but smaller than Neptune, orbiting a red dwarf about 120 light-years away. In 2023, observations detected water vapor in its atmosphere, along with possible signs of dimethyl sulfide, a gas that on Earth is only produced by marine phytoplankton. If confirmed, that would be an incredibly strong biosignature. But the planet is probably too large and too hydrogen-rich to be truly Earth-like. It might be more like a smaller version of Neptune, with a small rocky core surrounded by a thick hydrogen atmosphere and perhaps a high-pressure water ocean beneath. Not the kind of world we're used to thinking about as habitable, but possibly habitable nonetheless. Each of these worlds, and dozens more in the catalog, represents a potential home for life, and the list keeps growing. When the first exoplanet was discovered in 1995, it seemed almost miraculous that we could detect planets around other stars at all. The idea that we'd ever know details about these worlds, their sizes, their masses, their atmospheric compositions, seemed like pure fantasy. Yet, here we are, 30 years later, not only detecting thousands of exoplanets, but measuring their properties with remarkable precision. We know their densities, which tells us whether they're rocky or gaseous. We know their orbital periods and distances from their stars. We're measuring their atmospheric compositions, identifying specific molecules in their air from dozens or hundreds of light years away. The James Webb Space Telescope has revolutionized what's possible. Launched in late 2021, Webb is specifically designed to study exoplanet atmospheres with unprecedented sensitivity. It can detect the faint spectral signatures of gases like water vapor, carbon dioxide, methane, and ammonia. It can potentially identify biosignatures if they're present in sufficient quantities. And Webb is just the beginning. The next generation of telescopes currently being planned and built will take this even further. The extremely large telescope, under construction in Chile with a mirror 40 meters in diameter, will be able to directly image some nearby exoplanets, actually photographing them as individual points of light separate from their stars. The Habitable Worlds Observatory, a proposed NASA telescope that would launch in the 2040s, is specifically designed to directly image and characterize Earth-like planets around Sun-like stars. It would be able to photograph dozens of potentially habitable worlds and analyze their atmospheric compositions in detail. Within a few decades, we might have actual photographs of planets like Proxima Centauri b or TRAPPIST-1e. Not artistic renderings or computer simulations. Actual images captured by telescopes. We might see blue oceans and white clouds. Green continents if photosynthetic life has colonized the land. Brown deserts, white ice caps. We might watch seasonal changes as planets orbit their stars. Vegetation blooming and dying back in annual cycles. We might even detect artificial lights on the night sides of planets, the glow of cities powered by alien civilizations. When astronomers analyze light from exoplanet atmospheres, they're looking for biosignatures, combinations of gases that are difficult to explain without invoking biology. The strongest biosignature we know of is oxygen and methane together in an atmosphere. These gases react with each other rapidly in geological terms, destroying each other within thousands of years. On Earth, oxygen comes primarily from photosynthetic organisms like plants and algae. Methane comes from bacteria in wetlands, in the guts of animals, and from human activities. Without life constantly replenishing both gases, they would disappear from Earth's atmosphere in a geological instant. If we find an exoplanet with both oxygen and methane in significant quantities, that would be very hard to explain without life. Another strong biosignature is an ozone layer. Ozone is a form of oxygen with 3 atoms instead of 2, and it accumulates in the upper atmosphere where ultraviolet light from the sun breaks apart oxygen molecules that then recombine into ozone. On Earth, our ozone layer protects the surface from harmful UV radiation and is a direct consequence of the oxygen produced by photosynthesis. An ozone layer on an exoplanet would strongly suggest oxygen producing life. Even more exotic biosignatures might exist for technological civilizations. Industrial pollutants like chlorofluorocarbons don't exist naturally anywhere in the universe as far as we know. They're entirely synthetic, created through industrial chemistry. If we detected CFCs in an exoplanet's atmosphere, that would be a technosignature, proof of industrial civilization. Similarly, we might be able to detect reflected light patterns that indicate vegetation. Plants on Earth reflect light in very specific ways, particularly in the near-infrared part of the spectrum, where chlorophyll strongly reflects to avoid overheating. This creates what's called the red edge, a sharp increase in reflectivity at certain wavelengths. If we observed similar patterns from an exoplanet, it might indicate photosynthetic life, though we'd have to be careful because minerals can sometimes create similar patterns. All of these detection methods bring us to one of the most profound questions in human history. Where is everyone? We've found potentially habitable worlds aren't rare. They appear to be common. We've discovered them around the nearest stars to our Sun. Extrapolating to the entire Milky Way galaxy with its 100 billion to 400 billion stars, there could be billions of potentially habitable planets in our galaxy alone. Billions of worlds with liquid water, stable temperatures, protective atmospheres. Billions of places where life could arise. And yet we see no evidence of other civilizations, no radio signals, no megastructures, no spacecraft visiting Earth, no obvious signs of stellar engineering or Dyson spheres. The galaxy appears to be silent. This is known as the Fermi paradox, named after physicist Enrico Fermi, who supposedly asked, "Where is everybody?" during a lunch conversation in 1950. If life is common, if intelligence is a natural outcome of evolution, if technological civilizations inevitably arise, then some of them should be millions, or even billions of years older than us. They should have had ample time to spread throughout the galaxy, colonizing star system after star system. We should see evidence of them everywhere, but we don't. So either life is extraordinarily rare, arising on only a tiny handful of planets in the entire galaxy, or intelligence is rare, with most biospheres never evolving complex nervous systems and problem-solving abilities. Or technological civilization is rare, with most intelligent species never developing science and engineering. Or technological civilizations inevitably destroy themselves before spreading to the stars. Or they're deliberately hiding from younger civilizations like us. Or we're the first, the earliest technological civilization in the galaxy's history. Or they're already here, observing us, and we just haven't noticed. Each explanation has profound implications, and we genuinely don't know which one is correct. Finding microbial life on another world would actually be somewhat bad news in terms of the Fermi paradox, because it would suggest that the origin of life is relatively easy, that it happens frequently throughout the universe. If life arises easily, but we still don't see technological civilizations, that would imply something prevents life from reaching advanced stages. Some filter, some barrier that civilizations can't cross. This is called the Great Filter Hypothesis. The idea is that there's at least one extremely improbable step in the path from lifeless planet to galaxy-spanning civilization. A step so difficult that almost no one makes it through. The question is whether that filter is behind us or ahead of us. If it's behind us, if the hard step was the origin of life itself or the evolution of complex cells or the development of intelligence, then we're lucky. We're one of the rare success stories. We've already passed through the filter. The galaxy might be full of planets with simple microbial life but almost no technological civilizations, and we're one of the precious few that made it. But if the great filter is ahead of us, if it's something that happens to technological civilizations after they reach our current level of development, then we're in trouble. It might mean that civilizations inevitably destroy themselves through nuclear war, ecological collapse, artificial intelligence gone wrong, or some other catastrophe we haven't even imagined yet. Finding evidence of dead civilizations would be even worse news. Imagine if we detected artificial structures on an exoplanet, clear signs of cities and technology, but no radio signals, no signs of current activity, just ruins. That would suggest that reaching technological advancement isn't the hard part. Surviving it is. Then there's the timeline problem, and it's one that doesn't get discussed enough in popular conversations about extraterrestrial life. Even if intelligent civilizations exist on the planets we've found, even if someone is home on Proxima Centauri b, or TRAPPIST-1e, or LHS 1140b, we're separated by vast gulfs of space that light itself takes years or decades to cross. Communication with Proxima Centauri b would have a minimum delay of 4.2 years each way. You send a message. 4.2 years later, it arrives. If they immediately respond, you receive their reply 4.2 years after that. That's an 8.4-year minimum for a single exchange. A conversation where each response takes nearly a decade. For TRAPPIST-1e, the delay would be 40 years each way, 80 years for a single exchange. You could ask a question as a young adult and receive the answer as a senior citizen if you live that long. For Kepler 452b, 1400 light-years away, the delay is 1400 years each way. 2800 years for a conversation. You send a message today, and the reply arrives in the year 4825, assuming anyone receives it and responds immediately. Human civilization might not even exist anymore by the time a reply arrives. The Roman Empire, the medieval period, the Renaissance, the Industrial Revolution, 2 world wars, the Information Age, all of recorded human history, could fit into the time it takes for a single message exchange. And that's assuming they respond immediately and the message travels at light speed with no delays or errors. In reality, they might need years or decades to decode the message, debate how to respond, craft a reply. The actual time for meaningful communication could be thousands of years. This temporal isolation is just as profound as the spatial isolation. We're not just separated by distance, but by time itself. But despite all these challenges, despite the vast distances and communication delays and uncertainties, the search for life on these worlds matters profoundly. It's not really about finding aliens to talk to, though that would certainly be incredible if it happened. It's about understanding our place in the universe. Every potentially habitable planet we find helps us understand the conditions necessary for life. It tells us whether Earth-like worlds are rare or common. It reveals the diversity of planetary environments that exist. It constrains the parameters of where life can arise and survive. Each discovery narrows down the vast space of possibilities. Before we discovered any exoplanets, scientists could only speculate about whether other planetary systems existed. Some thought they might be rare, special products of unusual circumstances in the early solar system. Now we know planets are everywhere, probably outnumbering stars in the galaxy. Before we started finding Earth-sized planets in habitable zones, we didn't know if such worlds existed. Maybe planetary formation always produced gas giants and barren rocks, but nothing in between. Now we know Earth-sized worlds in habitable zones are relatively common. We've found dozens of them, and we've barely started looking. Each answer leads to new questions, and each question refines our understanding. The search for habitable worlds also directly informs our search for life in our own solar system. Jupiter's moon. Europa has a global ocean beneath its icy crust, kept liquid by tidal heating from Jupiter's immense gravity. Saturn's moon Enceladus has a similar subsurface ocean, and it's actively spraying water into space through geysers at its south pole. Titan, Saturn's largest moon, has lakes and rivers of liquid methane on its surface and possibly a water ocean deep underground. These are potentially habitable environments in our own cosmic neighborhood, places we could reach with robotic probes within our lifetimes. If we find life on Europa or Enceladus or Titan, if we discover that life arose independently multiple times in a single solar system, that would dramatically increase the probability that life exists on exoplanets as well. Conversely, if we explore these worlds and find them lifeless despite having the right chemistry and energy sources, that would suggest life is harder to start than we thought, which would inform our estimates of how common it might be around other stars. The philosophical implications of this search cannot be overstated. For all of human history, we have wondered whether we're alone in the universe. It's one of the oldest questions our species has asked. Ancient Greeks debated whether other worlds existed. Medieval scholars argued about the plurality of inhabited worlds. Every culture has myths and stories about beings from the sky. And now, for the first time in human history, we have the technological capability to actually answer this question. Not through philosophy or theology or speculation, but through observation and measurement and science. We can point our telescopes at other worlds and look for signs of life. We can analyze their atmospheres and search for gases that shouldn't be there without biology. We can measure their properties and determine whether they're suitable for life as we know it. Finding habitable planets forces us to confront our cosmic loneliness. If we eventually confirm that we're alone, that Earth is the only world in the observable universe that hosts life, that would be simultaneously profound and terrifying. It would mean we're the universe's only voice, the only witnesses to its grandeur, the only beings capable of understanding it. That's an enormous responsibility. If we're alone, then the fate of life in the universe rests entirely on our shoulders. If humanity destroys itself, if we succumb to nuclear war or climate catastrophe or any of a dozen other existential risks, then the universe returns to being lifeless and meaningless. All the beauty and complexity that evolution created over billions of years, snuffed out, never to return. But if we're not alone, if we share the universe with other intelligences, that's equally profound. It would mean we're part of a larger cosmic community, even if we never communicate with them directly. It would mean the processes that created life on Earth are universal, that given the right conditions and enough time, the universe naturally gives rise to complexity and consciousness and wonder. It would fundamentally change how we see ourselves. We'd no longer be the pinnacle of creation, the only intelligent beings, the only ones who matter. We'd be one species among many, one voice in a cosmic chorus. That requires humility, but it also offers hope. If others have survived and thrived for millions or billions of years, then perhaps we can too. Perhaps the challenges we face are not insurmountable. Perhaps there's a path forward that we just haven't found yet. The question of when we might find life is more complicated than it seems. Many scientists believe we could detect biosignatures on exoplanets within the next 10 to 20 years, if they exist and if they're strong enough. The James Webb Space Telescope is already capable of detecting some biosignatures on nearby planets with favorable conditions. Future telescopes will be even more sensitive. But there's a huge difference between detecting anomalous gases in an atmosphere and confirming they're produced by life. We'll need multiple independent lines of evidence. we'll need to rule out all possible non-biological explanations. We'll need to observe the planet over extended periods to see if the signals persist or vary in ways consistent with biology. The announcement of the discovery of extraterrestrial life will not come as a single dramatic press conference where scientists declare we've found aliens. It will come as a gradual accumulation of evidence, a slow building of confidence that the most likely explanation for what we're seeing is biological. Papers will be published suggesting possible biosignatures. Other scientists will critique those papers, proposing alternative explanations. Follow-up observations will be conducted. The scientific community will debate and argue and gradually converge on a consensus, or not converge, and the debate will continue for years. That's how science works, especially for extraordinary claims. And make no mistake, the discovery of extraterrestrial life, even simple microbial life, would be the most extraordinary claim in human history. It would require extraordinary evidence. But when that evidence does finally accumulate, when we reach the point where the scientific consensus says, yes, we've found life on another world, that will be the biggest discovery humanity has ever made. It will be front-page news across the globe. It will be taught in every school. It will be remembered thousands of years from now as the moment we learned we're not alone. It would immediately raise a cascade of new questions. How common is life? We've found it on one exoplanet, but is that typical or exceptional? How complex is it? Is it simple bacteria-like organisms or something more sophisticated? Can we learn anything about its biochemistry from the biosignatures? Is it based on DNA like Earth life or something completely different? Could we ever communicate with it if it's intelligent? And perhaps most pressingly, what does this mean for life in our own solar system? If life exists on nearby exoplanets, the probability that it also exists on Europa or Enceladus or Mars increases dramatically. We'd have reason to believe that life arises wherever conditions are suitable, not just on rare special worlds. The search for life would shift from a speculative endeavor to a practical one with clear targets and realistic expectations. But we also need to consider the possibility that we might not find life, at least not in the near future. We might observe hundreds of potentially habitable exoplanets over the next several decades and find all of them lifeless. Atmospheres in chemical equilibrium with no signs of biological processes, no oxygen-methane combinations, no ozone layers, no vegetation signatures, nothing but geology and photochemistry. That would also be a significant result, though a disappointing one. It would suggest that either life is indeed rare, arising on only a tiny fraction of habitable worlds, or that the biosignatures we're looking for don't apply to alien life. Perhaps life elsewhere uses completely different biochemistry that doesn't produce the gases we're searching for. Perhaps photosynthesis as we know it is rare, and most biospheres are dominated by organisms that don't produce oxygen. Perhaps technological civilizations are common, but they're careful not to pollute their atmospheres with detectable industrial chemicals. The absence of evidence wouldn't be evidence of absence, but it would force us to reconsider our assumptions. Despite all the uncertainties, despite the challenges and the vast distances and the communication delays, there's genuine reason for hope. We've gone from knowing about 0 exoplanets to over 5,000 in just 30 years. We've gone from not knowing whether habitable worlds exist to finding dozens of strong candidates. We've gone from having no way to study exoplanet atmospheres to detecting specific molecules in their air. The progress has been exponential, and there's no reason to think it will slow down.